Hi everyone! In this video, we're going to use the method of cylindrical shells to find the volume generated when the region between curves is rotated about the given axis. And the curves we have here are y equals x squared, so it's going to be parabola, and y equals x, so it's just a straight line. And we will be rotating the region about the line y equals 2. We're going to start by constructing this region. Okay, so the first function that we have is y equals x squared. It's the basic quadratic function and its graph is parabola. So the points will be x, y, when x is 0, y is 0. When x is 1 or negative 1, y is positive 1 in both cases, since I square them. And then when we have values 2 and negative 2 for x, y values are 4. Okay, so the points are 1, 1, negative 1, 1, and then 2, 4, negative 2, 4. Okay, so that's y equals x squared. And the second function is y equals x, so it's a straight line with points that have exactly the same x and y coordinates. So the points will be 0, 0, 1, 1, 2, 2, 3, 3, and so on and so forth. Okay, so I grabbed both functions, and where is the region? When I'm trying to locate the region, I always have to follow this rule. The region should be bounded only by the given curves and no other curves. So I should have a region that's only bounded by two lines, two curves. Well, I think it's this one over here. I can barely see it, but yeah, it's over here, this little tiny region. Now in the next step, I will need to construct a solid by rotating this region about the line y equals 2. So y equals 2 is the horizontal line that goes through 2 on the y-axis. Now, since this region is so small, I'm gonna redraw it. I'll make it larger, and it's very important to make large drawings. And then once I redraw it, then I will rotate it. Okay, so I think I'm gonna choose this scale. That's gonna be 1. This is gonna be 1. And now I will just resketch, or I will copy it here. So I do have a point of intersection here at 1, 1. Let's say it's here, and here's that straight line, and let's say that's going to be that curve. And now I'm rotating about the line y equals 2, so that's the axis of rotation. When I rotate this region about line y equals 2, well, it will appear on the other side of this line. So I'll start by just reflecting this region over the line y equals 2. So since it's going to be reflected, all points will be equidistant from y equals 2 on the other side. So this point at 1, 1, it's going to be reflected over here. So okay, here I have 2, 3, and then I'll put 4. Right here. So that's this point. Now this point will be 2 units away, so that's where it's going to be. And now I'll just have to sketch how it's going to look like on that other side. So I think it's good enough. So I reflected over this line y equals 2. And now for me to see that it's a 3D object, I will add some lines here, some like ovals. So I'll add one over here. That will create this hole in the object and on this side, like that. So now it's starting to look like a three-dimensional object. So once I obtain the solid, next I need to sketch a typical shell. Remember, we're using the method of cylindrical shells, so I'll say that it's step 3. Okay, so here I sketched just a picture of cylindrical shell just to remind you how looks like. So I like to think about it as like a wedding band. So it has thin sides, but it has some height to it. right? So it's not up like flat. And when I need to sketch a cylindrical shell within my object, within my solid, this is how I start. I start by placing a rectangle, typical rectangle or some arbitrary rectangle, in my region right here. And I have two choices as well when I start with. I can place rectangle vertically or I can place rectangle horizontally. So that's what I mean. So I can either place rectangle this way or I can place rectangle this way, so horizontally. And at this point I have to think, what's the right way to position rectangle, vertically or horizontally? Think that once you position it, you will have to rotate it the same way as you rotated the region, so about the line y equals 2. And in your mind, see what happens when you rotate the vertical rectangle. So I guess I should hold my pen right like this. So when I rotate a vertical rectangle versus when I rotate a horizontal rectangle, in which case will I get this kind of object? And it doesn't have to stand like that. It could be on the side, right? Well, to get an object with thin sides and some height to it, I have to rotate horizontal rectangle, right? So not this one, but horizontal. So I'll try that. Let's say my rectangle is over here. And keep in mind that this is an arbitrary rectangle. So I just picked a random spot within the region for that rectangle. And when we work with arbitrary objects or lines or rectangles like that, we'll say that, well, I chose it where? Well, it's some value y on the y-axis, right? I could place it lower or I could place it higher. So it would be corresponding to some number along the y-axis, right? So I chose it at y. Okay, now as I rotate it, it will appear on the other side, and then I will connect those two and I'll see the shell. Let's say it's here as I reflected, and now I will connect them. So I can see the shell. Well, a shell, because it's just some arbitrary shell. Like that. Okay, so do you guys see it? It's laying on the side, right? If I compare it to this picture, it's laying on the side. Now, why is this step important? Why do you want to sketch a cylindrical shell? Because to find the volume of the solid, we're going to use integration. So we're going to integrate a function, well, a function that represents the volume of a cylindrical shell. And to set up that function correctly, I need to see the shell because I will need to talk about its radius, I will need to talk about its height. And this is how this integral is going to look like in general. So we'll have limits of integration, we'll talk about them in a minute, but within the integral we'll have to have the following structure. So it's going to be 2 pi times r, which is the radius of a shell. Radius of a shell, of an arbitrary shell, and h is the height of that arbitrary shell. And here we'll either have dx or dy. So depending on the situation, we either have to integrate in terms of x or in terms of y. Okay, so that means that now we have to get all those pieces together and set up the integral that will find volume for the object here. We'll start with determining the variable of integration. That's super important, and that's actually has to be the first thing you do. So variable of integration. In other words, x or y. It's going to be dx or dy. Now this is how you think about it. On this picture, I have a typical shell. I could create different shell if I made slightly different choice of the rectangle. If I put it lower or higher within this region, the shell would look different. Let's say if I put rectangle a little bit lower, then the shell itself would be wider and, I don't know, maybe a little bit taller or shorter. So again, it depends. But it will have slightly different shape or size, I should say, right? And that means that size of the shell depends on the position of this typical rectangle along the y-axis. So when I put it higher or lower, so if I move up or down with this sample rectangle, shell changes its size. So it means that the size of the shell depends on y, or on the position of this rectangle along the y-axis. Since it depends on y, that means that variable of integration will be y. And that's how you think about it. Just move the rectangle if you find yourself moving it up or down, and that's what happens when you have horizontal rectangle, right? It's pretty intuitive. Then you're integrating in terms of y. Everything depends on y. If you happen to have vertical rectangle, then it makes sense to move it right and left. So that's where its position depends on x, and you're integrating in terms of x. Okay, so that's variable y for us. Now, second, let's talk about the radius of the shell. Radius. And that's where usually most mistakes happen. To correctly express radius, you want to draw it. So don't do that without looking at the radius. So let's try it. Here's the shell, or a shell, arbitrary shell. I'm gonna sketch a radius. Where's gonna be the radius? Radius will always stretch from the center of the shell, and then center of the shell will be the axis of rotation. So from here to that typical rectangle, to the side of the shell, and go to the direction of your original region. So from here to here, that's going to be the radius. I know that from the x-axis to this place, so from here to here, that is exactly 2 units, right? And no matter what shell I pick, it's always going to be 2 units. And obviously that's longer, more than the radius is, right? The radius is shorter. But how much is it shorter? Well, it's shorter by this portion over here, right? So if I take 2 and I remove this portion, then, well, what is that portion? It's from the x-axis to the rectangle. Then I will get exactly the radius of that arbitrary shell, right? But how do I express this segment? Well, it goes from the x-axis to the rectangle, to the arbitrary rectangle, which I said that I position at y. So it means that it's exactly the same distance as here, right? So it means that its distance is y units. And see, as I move it up or down, and I change this y value and it becomes more or less, well, this distance is going to change together with this value y, right? And now I can see how I can express that radius. So I have to take 2, so I'll go all the way to positive 2, or 2 units, and then subtract this piece, which is y units. That's what radius is going to be. It's 2 minus y. Okay, so we got that, we got dy. And now we need to talk about the height. The height of the shell. Well, height of the shell exactly the length of this rectangle, right? And this rectangle is bounded by 2 curves. Well, this curve that was given to us, this is y equals x squared, and this line, y equals x. So we already know that to express the length of this segment, we have to take the right curve, or function describing the right curve, and subtract the function that describes the left curve on the left. So right minus left. And now here's another important note. When we made up our mind as far as what the variable of integration is going to be, at this point we had to say, or to note to ourselves, that since variable of integration is y, it means that everything in this integral will be written in terms of y. We shouldn't see any x's. And now, as I'm talking about the height of this rectangle, well, actually the height of the shell, which is the length of this rectangle, I'm gonna express it as the right function minus the left function. However, these functions have to be written in terms of y. So if they're not given to me in terms of y, let's say this one is not, right? It's given in terms of x. I have to rewrite it. So the height of the shell will be right function minus left function, and let's rewrite right functions as we need them. So the quadratic function y equals x squared, I'm going to rewrite as, so I'll just have to square root each side. And in this case, I get both positive and negative square root of y, but since we only have portion that's above the x-axis, is just simply x equals square root of y, the positive one. Okay, so it means that the function that's on the right is square root of y minus, and then function on the left is the line y equals x, but here I don't really need to do any steps, right? It's y equals x or x equals y. So it's simply minus y. Okay, so I'm writing it here. It's square root of y minus y. Well, that's what we have. Oh, and then the limits of integration, right? Well, let's start writing down the integral, and we'll talk about the limits of integration. So to find the volume, we'll set up the integral. Now here we have a constant 2 pi, and that constant I will place in the front of the integral sign, 2 pi integral sign. Now, when we talk about limits of integration, they also have to be consistent with the variable of integration. So I have to take them from the y-axis. And the way I think about it is that, again, I'm going to move this in my mind, move this sample rectangle up and down, and what is its lowest position and what is highest position that I can achieve. Well, from 0 to 1 along the y-axis, right, within this region from 0 to 1. So from 0 to 1, and now I have to write down r radius, so that's expression 2 minus y. It's an expression. It has to be multiplied by something else, so it's important to keep it inside the parentheses, 2 minus y. And then times h, which is the height of the shell. It's that expression here, so another set of parentheses. And then dy. Okay, so here's that integral, and I would say that the hardest part is behind us, so what's left to do is just to integrate that. But setting up this integral correctly, of course, is very, very important. Okay, so how do we integrate this? I know that I'm not going to even attempt integration until I simplify this expression. And to simplify it, I simply have to multiply out those two expressions. And when I multiply them out, since I have square root here, well, I will rewrite it as y to the power 1/2. Like that. So as I multiply expressions out, I will be using that power. So it's 2 pi integral from 0 to 1, and let's see what we can get. So 2 times y to the power 1/2. I'm starting this way. So it's 2y to the power 1/2 minus 2y, and then minus. Now I'm doing those two. Okay, so here it's y times y to the power 1/2. I have to add powers. 1 plus 1/2, that is 3/2. Negative times negative gives me positive, plus y squared dy. So once you multiplied out the expressions, then you have a sum or difference of terms, and we know that to integrate that, we just simply integrate each term. And we'll use same rule for all of them. So it's 2 pi. So we'll have to adjust the powers, right? So it's 2 times y to the power. Remember, we have to add 1 and divide by that number. 1/2 plus 1 is 3/2. And I'm dividing by 3/2. Minus 2 times power 1, 1 plus 1, 2, y squared over 2, minus y to the power 3 over 2 plus 1. 3 over 2 plus 1, that's same as 3 over 2 plus 2 over 2, which is 5 over 2. Okay, so that's going to be y to the power 5 over 2 divided by 5 over 2. Plus y plus 1 to the 3rd power over 3. Okay, and that has to be evaluated at 1 and 0. 2 pi times. Let's see. To divide by 3 over 2, that is same as to multiply by 2/3. So 2/3 times 2 gives me 4/3, y to the power 3/2. Now 2 and 2 will cancel, so it's minus y squared. Here I'm dividing by 5 over 2, that's same as multiplying by 2 over 5 times y to the power 5 over 2, plus I'll just write 1 over 3 times y cubed, evaluated at 1 and 0. Okay, so good news, we have easy numbers to plug in. So when I'm plugging in 1, I'll get, that's, these are all y's become 1s, right? So I'll just have their coefficients left. 4/3 minus 1 minus 2 over 5, and then here plus 1 over 3. That's when I plugged in 1 in all of those. And then as I plug in 0, so I have to put minus, and then I have to plug in 0, but since each term has y, all that is going to turn into 0, so it's just simply minus 0. Okay, perfect. And I should be able to combine all those fractions. Let me just right away think about the LCD. So I'll put 1 over 1. The LCD is 15, right? So times 5 times 15 times 3 times 5, and that's 0. Okay, so I'll have 2 pi times 20 minus 15 minus 6, and then plus 5 over 15. 2 pi times, okay, so 20 minus 15 is 5. 5 plus 5 is 10. 10 minus 6, 4. Okay, so I think it's 4 over 15. And of course I can multiply that, and I can say that it's 8 pi over 15. Good news, I got a positive number, so that increases the chance of that being the right answer. If I get a negative number, that's a red flag. Volume cannot be negative. So if you ended up with something negative when you're finding volume, go back and recheck, well, maybe starting from step 1. And then one more time, I want to emphasize that it's very important to have a large picture so that you can see what's going on with your picture. It's very important to sketch a shell, a typical shell, and identify its radius and height by looking at the sketch, not guessing, because there are a lot of different cases how everything can be positioned. So try to go off your picture.